So today we'll be discussing the ideal gas equation. If you remember from our last video, we talked of the basic principles that govern the kinetic molecular theory, and there were three main basic principles that we discussed. The first one was that every substance is made up of particles called molecules. These molecules are in constant random motion. And then the third principle that we looked at was that these molecules interact amongst themselves. But then it makes it very difficult for us to look at the thermodynamic parameters that affect this gas if we assume that the molecules within this gas are in constant random motion, which we cannot predict. As a result, scientists came up with the idea of the ideal gas. So when we talk of the ideal gas, it basically gives us an idea of how the thermodynamic parameters are affecting this gas. It makes it easy for us to study this gas if we assume, if we talk of the ideal gas and make an assumption. The assumption that we are making for an ideal gas is that an ideal gas is a gas in which molecules do not interact amongst themselves. This is the simplest definition because it basically kills the third basic principle that we looked at when we talked of the kinetic molecular theory. We know that in actual sense molecules do interact amongst themselves, but for studying purposes and for scientists to understand what is happening to a gas, we assume that these molecules do not interact amongst themselves. The only interaction that we are assuming is occurring when molecules interact is that of perfect elastic collisions. An example I would give is when you shoot a ball on a pool table, the balls begin to hit, to bounce and hit each other in perfect elastic collisions. That is what we are assuming is happening to molecules within a gas. So this idea links the three main thermodynamic properties that affect a gas, which is the pressure, the volume, and the temperature. So our job today is trying to derive or see where this equation is coming from. So our job today is basically looking at how to derive the ideal gas equation, which is the link between the three main thermodynamic parameters that affect a gas. If you remember the last time we looked at the kinetic molecular theory, we derived the formula for the pressure of molecules within a gas. This is where we're going to start from because things in physics are interlinked. You remember well, we said, let me write this here. If you remember well, we derived the formula for the pressure of molecules within a gas to be 1/3 times the number of moles multiplied by the mass times v squared. Basically, this v squared here, this is meaning squared, is what we call the mean square velocity. The mean square velocity. In Russian, it would be written as VKV. Basically, we are referring to the mean square velocity when we talk of this v squared. From here, what we're going to do to our equation is that we're going to use this equation. We're not going to change anything, but we're going to multiply this by 2 and by 2. This is still the same thing. If we cancel out, they will still remain with the 1. But then when we take this mass multiplied by this v squared and these 2 here, we have, if you remember well, we have the kinetic energy. Because kinetic energy is mass multiplied by the velocity squared over what? 2. And then this mean square velocity is calculated using the formula v square is equal to the square root of 3 multiplied by the Boltzmann constant over the what? Over the mass. So from here we can take this one and replace it into our equation for kinetic energy, and then we're going to obtain something like kinetic energy becomes equal to m, which is the mass, over 2 multiplied by the square root of 3k t over the mass. Not forgetting that this is squared, so we're going to square this. The square root and the square cancel themselves out. The mass and the mass cancel each other out. Therefore, we remain with is equal to 3 Kete over 2. From here, what we've done here is, this here gave us, when we go back to the equation for pressure, this here gave us the kinetic energy. So when we take this and replace it in our equation, we are going to obtain something like pressure is equal to 2 over 3, this 2 that we had remaining here, multiplied by this 3 over 2 that we are now having, times the Boltzmann constant, times the temperature, multiplied by the number of moles. So from here we can easily say that these cancel themselves out. We're going to remain with let me use a green marker. Pressure now becomes equal to the number of moles multiplied by the Boltzmann constant times the temperature. So we keep note of this equation. And then, let me rewrite this equation here for simplicity's sake. We're going to say pressure is equal to the number of moles multiplied by the Boltzmann constant times the temperature. From here, if you remember well, we know that the number of moles is equal to the number of molecules over the volume. The number of molecules that is contained within a gas multiplied by the volume, divided by the volume of that gas will give us the number of moles. So basically from here, we can remember that the number of molecules is now equal to the same number of moles, so that we were just using a different symbol here so that we do not mix the two. The same number of moles now multiplied by the Avogadro's constant. This n on top here, the number of molecules now is now found by the number of moles. We've just used a different symbol to differentiate these two, but they're talking about the same thing. So now we have the number of moles multiplied by the Avogadro's constant, representing the n over the volume that we have. From here, we can now replace this, what we found here, the number of moles multiplied by the Avogadro's constant over the volume. We can replace it back into the equation for pressure, and we are going to say P is now equal to the number of moles multiplied by the Avogadro's constant times the temperature, times the Boltzmann constant times the temperature over the volume. This multiplied by this, it gives us PV is now equal to the number of moles times the Avogadro's constant multiplied by the Boltzmann constant times the temperature. This relationship that we obtain here, where we're having the Avogadro's constant multiplied by the Boltzmann constant, gives us what we are calling the universal gas constant, which is represented by the letter R. So we can now replace this. This is giving us R. We can now finally say pressure multiplied by the volume is equal to the number of moles multiplied by the universal gas constant times the temperature. From here, if you remember what our task today was, the task was for us to derive the equation, the ideal gas equation. And at the beginning, we wrote what the ideal gas equation is. We said the ideal gas equation is pressure multiplied by the volume is equal to the number of moles multiplied by the universal gas constant times the temperature. So basically here is our equation, our ideal gas equation. But in some books, this here, like I said, is the number of moles. The number of moles is basically represented by, in some books it is represented by the letter N. So in some books you might find that the ideal gas equation is written like this. It is the same thing, these are representing the same thing. If you want to go further, you can rewrite this number of moles as pressure is equal to, pressure times volume is equal to the number of moles, remember, is the mass of the substance over the molecular mass times RT. So here is our ideal gas equation, which is linking the three thermodynamic properties of a gas, or the thermodynamic parameters of a gas, which is the pressure, the volume, and the temperature. So basically that is it today. We've derived the ideal gas equation.